Good day, students. Today we are going to start with a new topic, electrochemistry. In this topic, we are going to study the different types of electrodes. The first electrode we are going to study is the gas metal ion electrode. Example under this is the hydrogen gas electrode. Hydrogen gas bubbling in a solution of an acid comprises the construction of the hydrogen gas electrode. The electrode is represented in the following way. We have platinum wire or platinum metal which is in contact. This is for electrical contact because it is a gas electrode and gas is a non-conductor. So in order to conduct, we require a metal. So platinum wire is used only for electrical contact. Then we have in contact with this platinum wire, we have the hydrogen gas which is bubbling or which is bubbled into the solution of H plus ions. H plus ions come from the acid and it is in the aqueous form. So this is how we represent the hydrogen gas electrode. Platinum wire, hydrogen gas, H plus ion. The line here, the slash that we put or a vertical line that is put there indicates that they are in contact. Platinum wire is in contact with the hydrogen gas which is in contact with the H plus ions from the solution. Electrode reaction. Electrode reaction is written in this way. We have hydrogen gas in equilibrium with H plus ions. We have 2H plus ions because we have to balance this 2. Hydrogen is written as H2. So there are 2 H ions. So we write this as 2 here. And when we write 2, whenever an ion is formed, an electron will be given out. So if there are 2 H plus ions, there will be 2 electrons which will be given out. This reaction is the oxidation reaction. In an oxidation reaction, electrons are given out. And this electrode is reversible with respect to the H plus ions. This electrode is said to be reversible with respect to the H plus ions from the solution. Whenever we study about electrodes, we have to know how to represent the electrode, how to write the electrode reaction. Now gas, as I have said, is non-conducting, hence platinum, or you can use any other metal also which is not attacked by the acid which is used there. This is the diagram of the hydrogen gas electrode. We have a container, say a beaker, in which we have the H plus ions. Now the H plus ions which are in the aqueous form, the concentration has to be maintained as 1 molar. So this is about the solution. So it is an acid which has a concentration of 1 molar. Now the hydrogen gas from a cylinder at 1 atmosphere pressure has to be bubbled into a solution. So we have this electrode which is constructed using a glass tube which has an opening here for the gas to enter. So the hydrogen gas which enters here has to be at 1 atmosphere pressure, and it enters and it is bubbled into a solution. At the lower end it is open here, and there is another hole on either side, this side and the other side also, for the hydrogen gas to escape, to come out, to bubble out. Now inside here we have a platinum wire. You can see a platinum wire which is attached to a platinum foil. Now this hydrogen gas which enters here to this opening, it is in equilibrium with the H plus ions from the solution on this particular platinum foil. So if you maximize this view, it is like this. That is, we have, this is a hydrogen gas which is bubbled, and this hydrogen gas, when it gets oxidized, it will give out electrons. So we have electrons here and the H plus ions in the solution. So this equilibrium continues. Okay, it is maintained on the surface of the platinum foil inside this electrode. So this reaction, it is called as a half cell reaction or half reaction at the platinum surface. That is, H plus ions will take up the electrons and give you the hydrogen gas, or the vice versa. Hydrogen to give us 2 H plus ions plus 2 electrons. This reaction which is written here, 2 H plus ions aqueous plus 2 electrons to give hydrogen gas, this is a reduction reaction. That is, the H plus ions are taking up the electrons and they are getting reduced to hydrogen gas. If you write the reaction in the opposite direction, that is, hydrogen gas to give the H plus ions and the electrons, that will be the oxidation reaction. So we have hydrogen gas at 1 atmosphere pressure is in equilibrium with the 2 H plus ions from the solution plus 2 electrons. So whenever electrons are given out, it is nothing but an oxidation reaction. Whereas this reaction that is written here is the reduction reaction. So the electrode can be used as an oxidation electrode and as a reduction electrode in any cell. A similar diagram, we have the hydrogen gas at 1 atmosphere pressure which enters the side tube into the glass tube which has holes, you can see here, which has holes to let the bubbles of hydrogen gas to escape. We have the platinum electrode, that is the platinum foil, this is the platinum wire, and a solution containing 1 moles per liter solution, that is 1 molar solution of H plus ions. So this is nothing but a hydrogen gas electrode. If you are asked to draw, this is the way how you have to draw it. This diagram explains how the hydrogen gas enters the tube, hydrogen gas tube, and it bubbles out, and there is an equilibrium maintained on this platinum foil. Now this standard hydrogen electrode is used as a standard electrode or a primary reference electrode. when it is used as a primary reference electrode, the potential of this electrode is arbitrarily fixed as 0 volt. So whenever hydrogen gas electrode is used, the potential of this is taken as 0 volt. This is very important. I want you to remember this. Anytime the hydrogen gas electrode is used, you have to remember the potential of this electrode is equal to 0. The potential, we usually write it in the form of EMF, potential of the standard hydrogen electrode is equal to 0 volt. Now, what are the advantages and disadvantages of using hydrogen gas electrode? Advantages would be that the potential of this is fixed as 0, and any other electrode combined with this electrode, whatever EMF is obtained is directly the potential of that particular electrode. Disadvantages are many. Platinum foil is susceptible to contamination. It is easily poisoned by the impurities which are present in the gas as well as the HCl solution. Therefore, it has to be cleaned and replenished virtually before every measurement. So every time you are using the hydrogen gas electrode, you have to clean the platinum foil. The second disadvantage is, for accurate measurements, pressure must be controlled. Third, dealing with the hydrogen gas in pressure cylinders is a risky job. That is, every time you are using the hydrogen gas electrode in your laboratory, you have to have a hydrogen gas cylinder next to you. Next disadvantage, it is rather difficult to regulate the pressure of the hydrogen gas to be at exactly 1 atmosphere throughout the experiment. Every time you are making the measurement, at every step you have to make a note that the pressure remains at 1 atmosphere. So you have to regulate the pressure. So it is again a difficult task. Next disadvantage is, it is difficult to maintain the concentration of HCl at 1 molar. This concentration, as I have told you earlier, has to be maintained at 1 molar throughout your experiment. So next we have the other gas electrodes, that is the oxygen gas electrode and the chlorine gas electrode. We will take up the chlorine gas electrode. We have the chlorine gas which is bubbled into a solution having the Cl minus ions here. It's not the H plus minus ions as in the hydrogen gas electrode. In the chlorine gas electrode, it is the Cl minus ions which are present in the solution. So we have the reaction Cl minus, aqueous means it is in the solution form, in equilibrium with the chlorine gas plus an electron. You could also write this reaction how you have written for hydrogen gas. That is, we have chloride ions in equilibrium. This is aqueous in equilibrium with chlorine gas plus an electron. So here there is two to balance that we can write 2 Cl minus ions and 2 electrons. Now many a times when we ask the students to write this equation, they usually write like this. They write chlorine gas to give 2 Cl minus ions plus 2 electrons, because for hydrogen gas we write hydrogen gas here and we write H plus ions plus 2 electrons. Now that H plus ion, that is a plus, and the electrons are negative. We cannot have negative charges on the same side, so it is not balanced. So this is not the way of writing the reaction. So you have to write chloride ion is in equilibrium with the chlorine gas and the electron. Okay, so if you don't want to write half, then you have to multiply this and this by 2. When do we write half? In any cell reaction, whenever we require just one electron, then usually half is introduced. Otherwise, if you're just explaining about the chlorine gas electrode, you can give the reaction in this way, or you can give the reaction in this way. Next, the representation. As we have said, these are gas electrodes, so they are non-conductors. That is why we require platinum wire for electrical contact. So platinum wire is in contact with chlorine gas, is in contact with chloride ion. So we have the electrode reaction and electrode representation. This is the reaction and this is called as the representation. This electrode is reversible with respect to the chloride ions. Next is the hydrogen gas electrode. Oxygen gas electrode. Oxygen gas at a given pressure is bubbled through a solution containing what ions? Containing OH minus ions. So we have hydrogen gas. If I summarize hydrogen gas, we have the H plus ions in the solution. Chlorine gas, we have the Cl minus ions in the solution, and when it comes to oxygen gas, then it is the OH minus ions which should be present in the solution. So oxygen at a given pressure is bubbled to a solution containing hydroxyl ions. Now the reaction here is oxygen plus water plus 4 electrons in equilibrium with 4 OH minus ions. Okay, so we have OH minus ions which are in equilibrium, hence we have to introduce, we can't get H from oxygen, so we have it from water. Now 4 electrons. Why 4 electrons? We have Let's balance the reaction. This is O2. So I will just write here, we have O2 plus, say, water plus electron to give OH minus ions. Now let us balance this. We have O2, that is 2 and 1 here, so 3 oxygen. And look at the hydrogen here. This is 2 hydrogen. This is only 1 hydrogen. Suppose I put 2 here, so it is hydrogen is balanced. Look at oxygen. This is 2 and 1, 3 oxygen, and here there is 2 oxygen. So how do we balance it? Here there is 2 oxygen and here there is 3 oxygen. Suppose I put 2 here, then hydrogen also changes now. We have 2 2s are 4, so 4 hydrogen, and oxygen, let us see. So there are 4, let me just write it here. We have 4 hydrogen this side, and oxygen will be, this is 2 and 2, there are 4 oxygen. Okay, so if there are 4 this side, so I will have to write this, I will cancel out, and it will be 4 OH minus ions here. So it is perfectly balanced. So if there are 4 OH minus ions, to balance the charge, we have to have 4 electrons. Okay, so this is how we write the reaction for the oxygen gas electrode, and the representation. The representation is platinum, oxygen at 1 atmosphere. This has to be mentioned, and you have to mention it is a gas in contact with aqueous ions, aqueous O minus ions. The second type of, so all these electrodes that we have mentioned are the gas electrodes, gas metal ion electrode. The second type of electrode is metal ion electrode. Here the metal is dipped in its own ions. Metal is dipped in its own ions, hence the name metal ion electrode. The electrode representation is given by M/Mn plus, where M can be any metal. M can be any metal. So M is any metal. It can be zinc, it can be copper, it can be silver, it can be gold, or any metal. It can be aluminium, and so on. Okay, now this N is nothing but the valency. So N is the valency of the ion. If it is zinc, the valency is +2. If it is copper, the valency is +2. If it is silver, valency is +1. If it is aluminium, valency is +3, and so on. And depending upon the valency, that many electrons will be given out. So in this electrode reaction, we have the metal in equilibrium with the metal ions plus n number of electrons, So this is an oxidation reaction where electrons are given out. I can write the reverse of this reaction, and that will be the reduction reactions. For example, if I take, say, zinc electrode, If I take zinc electrode, if my metal is zinc, if I want to write the reaction, I will write it as zinc in contact with zinc ions plus 2 electrons. So whenever electrons are given out, it is the oxidation reaction. You have to get familiar with this term, oxidation and reduction. Suppose I write the reverse of this reaction, say Zn plus 2 plus 2 electrons to give you zinc. So this is nothing but the reduction reaction. Okay, so whenever electrons are given out in the reaction, it is oxidation. Wherever electrons are taken in, it is the reduction reaction. Similarly, we can write for aluminium. So we have aluminium metal in contact with aluminium ions Al plus 3. So how many electrons will be given out? 3 electrons will be given out. So this is your oxidation reaction. If you want to write the reduction reaction, it will be aluminium plus 3 electrons to give you aluminium. So this will be your reduction reaction. And so on. Now how do we represent this? This electrode, I can represent it this way. Aluminium is the metal, aluminium in contact with aluminium with its ions. This I can write as zinc in contact with zinc ions. Now this electrode, because the reduction is taking place, I can write it this way, Zn plus 2 slash Zn. It's a reverse reaction that is taking place. Similarly here, some books will write it as slash Al. Okay. We go to the next type of electrode, the metal insoluble salt anion electrode. Some books write it as metal insoluble salt electrode. It has a metal and it has a insoluble salt. A insoluble salt will be like AgCl, Ag2Cl2 and so on. And it has a common anion. The negative ion of the salt is a common anion in which this electrode is dipped. To understand it better, the electrode consists of a metal and a sparingly soluble salt. That is why we write it as insoluble salt, because it is a sparingly soluble salt of the same metal and it is in contact with a solution of a soluble salt. This anion which we have written here, it comes from a soluble salt, whereas here there is another salt which is insoluble. This anion comes from a soluble salt having anion common to this particular salt. For example, we have the calomel electrodes, a very important electrode which we use in the laboratory, and it is a secondary reference electrode. We have studied about hydrogen gas electrode, which is the primary reference electrode, and calomel electrode is the secondary reference electrode. In the laboratory, we don't make use of the hydrogen gas electrode, but we make use of calomel electrode all the time. So you have to know about the calomel electrode in detail. So it consists of mercury So the metal that is used there is mercury. Insoluble salt that is used there is solid mercurous chloride, that is Hg2Cl2. Mercurous chloride is Hg2Cl2. It is a solid, and this salt is also called as calomel. That is why the name comes as calomel electrode, and a solution of potassium chloride. So KCl salt is also used here, and you can see the anion of this salt and the anion of this salt are the same, but this salt is insoluble salt, whereas KCl is a soluble salt. Now, how is it represented? So the representation is usually written like this. We have mercury in contact with mercurous chloride, that is calomel, it's a solid, in contact with chloride ions in the aqueous form, in the solution form. So this KCl salt that we take, it is in the solution form. The reaction. This salt Hg2Cl2 will take up the 2 electrons, and we have Hg, which is mercury, plus 2Cl minus ions. So Hg2Cl2, the salt, insoluble salt, plus 2 electrons in equilibrium with mercury. I made a mistake here. Mercury is a metal which is in the liquid form. So this is not solid, it is in the liquid form. This mercury here also, it is in the liquid form, plus 2Cl minus ions. So this is the reaction which you have to know. So this is your reaction, and this is your representation. Okay, so reaction and representation, you have to know of all the electrodes. Now this electrode, the calomel electrode, the potential of this electrode depends upon the concentration of the KCl that is used there. This electrode is said to be reversible with respect to the chloride ions, and it depends, the potential of the electrode depends upon the concentration of KCl. So if the concentration is 0.1 normal KCl, then the potential is minus 0.3538 volts. If the concentration is 1 normal, then the potential is minus 0.2800 volts. And if we use saturated KCl, then the potential is minus 0.2415 volt. In our laboratory, we make use of saturated KCl. We don't use the other two concentrations. We use saturated KCl, and this is the potential that we have to remember in the case of calomel electrode. So the potential of the calomel electrode depends upon the concentration of KCl. In the laboratory, we make use of saturated KCl. So the potential of the calomel electrode will be minus 0.2415 volts. You have to remember this value. This would be the diagram to draw the calomel electrode. We have mercury here at the base. It is filled above mercury. So if this is mercury here, then above mercury is the paste. It is a paste of Ag2Cl2 . We need not put KCl there. It's a paste of calomel. So this Ag2Cl2 is calomel, and it is filled with the KCl solution. KCl solution can be 1 normal, it can be 0.1 normal, and it can be saturated KCl solution. In our laboratory, what we use is saturated KCl solution. And there is a small asbestos fiber, a small tip here which comes out, and here we have to fill this with the concentration of the desired KCl concentration, whichever is desired. In our laboratory, I have told you, we use saturated KCl. So this opening is to introduce, because it should not dry up, it should be filled up with saturated KCl. And then this is a wire to connect to the terminal of the potentiometer. So this is our secondary reference electrode, which we use in the laboratory. Chloride is used to maintain constant ionic strength. So you have to fill this and maintain the level of KCl. Now another example of this type of an electrode is silver chloride electrode. Silver chloride electrode is similar like that of the calomel electrode. So you should be able to write the reaction and the representation. It consists of a silver wire coated with a layer of silver chloride. This is inserted in a solution of KCl of known concentration. So I request you to write the reaction and the electrode representation. It is similar to that of the calomel electrode. Instead of mercury, you will have silver here. Instead of mercurous chloride, you will have AgCl, and the other soluble salt is KCl in both the cases. The next type of electrode, we have the redox electrode. Many electrode reactions involve only ionic species such as Fe+2 and Fe+3. The name redox tells us that the reduced and the oxidized species are present in the electrode. You can see here Fe+2 is the reduced species and Fe+3 is the oxidized species. So both are present in the same electrode. That is why it is called as a redox electrode. It consists of two different oxidation states of the same metal. Inert substance such as platinum is used for electrical contact. So when we have this electrode, we have platinum in contact with Fe+3 aqueous, Fe+2 aqueous. That is, It consists of two different oxidation states of the same metal. Now, since they are both in the aqueous state, we need a wire, inert substance such as platinum for electrical contact. So this is our electrode representation. An electrode reaction would be Fe plus 2 in equilibrium with Fe plus 3 plus an electron. So this reaction which is written here is the oxidation reaction. Fe plus 2 is getting oxidized to Fe plus 3, and when it is getting oxidized, an electron is given out. So whenever electrons are given out in a reaction, it is the oxidation reaction. Another important example here is the redox electrode. Redox electrode of hydroquinone. So it is called as the hydroquinone electrode. Electrodes, here this is an electrode with organic species. We have quinone and hydroquinone. In common language, we call it as the quinhydrone electrode. So we have quinone here. Sometimes we just write quinone in short as Q. So this is quinone molecule. Quinone plus this 2H plus comes from the acid which is present, plus 2 electrons will give quinhydrone. So quinhydrone we write as H2, we write it as H2Q. There are 2 H in addition to the quinone here, so we write it as H2Q. So this is quinone. In short, we write it as Q, and this H2Q we write it as hydroquinone. So this is a reaction for the hydroquinone electrode. We have an experiment here in the laboratory we do with this particular electrode. We take the solution, that is the acid solution here, that is the H plus, which we want to find out how much of this is present, and into this we add little of quinhydrone powder. We add about a pinch of quinhydrone powder. It's a black powder like charcoal. We put and we mix with this, and we dip a platinum wire here. So this is a platinum wire, and then this electrode is nothing but the hydroquinone electrode, because this is the equilibrium which takes place at that particular electrode. Now the redox electrode from organic molecules having two different oxidation states, that is quinone and hydroquinone. Platinum electrode dipped into a solution containing H plus ions and quinone. So we have, it is represented this way: platinum, then H2Q, Q and H plus ions in the aqueous form, and the reaction would be written as quinone plus 2 electrons plus 2 H plus to give H to Q. Limitations of the quinhydrone electrode. The quinhydrone electrode is not reliable for solutions above pH equal to 8. It is also unreliable in the presence of strong oxidizing or reducing agents which would disturb the equilibrium between quinone and hydroquinone. It is also subject to errors in solutions containing proteins or high concentration of the salts. The fifth type of electrode, we have the amalgam electrode. Here the metal is in the form of a amalgam. It is dissolved in mercury, the metal and mercury. Platinum is used for electrical contact. It is dipped in the amalgam. Mercury does not take any part in the chemical reaction. Example, here we have the sodium amalgam electrode. Now sodium amalgam electrode is represented in this way. We have sodium and mercury. Sodium and mercury forms the amalgam which is in contact with the sodium ions. Now sodium and mercury which form the amalgam, this mercury will not take part in the reaction. You need to know the concentration of sodium in this amalgam and you have to know the concentration of the sodium ions. C1 and C2 are the concentration of sodium metal in mercury, that is in the amalgam, and in the solution respectively. So if this is the representation, then how would we write the reaction? The reaction is written in a similar way as that of the metal-metal ion electrode. So we have in this case sodium from the amalgam which will give us Na plus ion plus an electron. The mercury does not take part in the reaction. So this is in the aqueous form. Now, there are many other electrodes, but this 5 we will consider as important for us. Now, next is the reference electrodes. Reference electrodes, as I have said, there are two types, primary reference electrode and secondary reference electrode. Primary reference electrode I have mentioned to you, it is your hydrogen gas electrode, and the secondary reference electrode I have mentioned to you, it is your calomel electrode. So if you are asked what are primary reference, which is a primary reference electrode, and if you are asked to explain, you have to explain the hydrogen gas electrode. If you are asked about the secondary reference electrode, then you have to mention about the calomel electrode. That's all for today, girls. I want you to learn all the reactions and the electrode representations, the description of all these electrodes. Thank you.